Okay, so now let's see an introduction idea for Bayesian analysis. And actually, previously we have seen the introduction session for the Bayesian analysis. Especially, we have said that there are two thoughts of schools in statistics: the Bayesian thoughts of school and that of the frequentist thought of school. So, but in most of the medical literatures, we have said that most of the medical literatures are overwhelmed by the frequentist approach. But there is also another way of just statistical analysis by the use of Bayesian methods, the Bayesian methods. The basic difference between the two, the Bayesian and the frequentist approach, is that the frequentist approach assigns the probability to the data, not to the hypothesis. Because we said that if you just interpret a p-value of 0.04, for example, the probability of getting the observed data, that means the result which is obtained from the collected data, the probability of getting the observed data purely by chance is 4% if the null hypothesis were true. This is the interpretation. So that the probability is assigned for the observed data. The probability is not assigned for it is not assigned for the hypothesis. Rather, the probability or the p-value or the probability is assigned for the observed data in the frequentist approach. It is not assigned for the hypothesis. But in the case of the Bayesian analysis, the probabilities are assigned for the hypothesis. The probability of the hypothesis to be true is this much percent in the case of Bayesian analysis. And in the case of frequentist analysis or frequentist statistics, the probability of the data to be true is this much percent, Or the probability of getting the observed data purely by chance is this much percent. So that the probability in the case of frequentist approach is assigned for the data, not for the hypothesis, And in the case of Bayesian analysis, the probability is assigned for the hypothesis, not for the data. That is the reverse. And furthermore, the Bayesian analysis also models by incorporating a prior knowledge or prior information. So in the Bayesian modeling or Bayesian analysis, we will have a prior distribution and a posterior distribution. The posterior distribution is the distribution or the probability that we obtained after the data is collected. And the currently collected data combined with the prior data or the prior information before the data is collected will be used in combination to estimate the posterior distribution. So that in the Bayesian analysis always there will be a prior distribution and a posterior distribution. But in the case of the frequent statistics, there is always a posterior distribution only. There is no prior distribution in the case of frequentist approach. So that is a clear difference between the two, So frequentist statistics is all about probability in the long run. The data set collected and analyzed is one of the many hypothetical data sets addressing the same question. You see, there are infinite number of possible data. Out of that infinite possible number of data, the one is that we have collected. The collected data is the one out of the possible infinite number of data, So that the p-value or the probability is assigned for the probability of getting the observed data purely by chance if the null hypothesis were true. So the collected data in the frequentist approach is one of the many hypothetical data sets addressing the same question. And uncertainty is due to sampling error alone. You see, variation among different data set results is occurred because of sampling variation, Because of sample to sample variation, if you do have if you want to just calculate the mean age of a certain class, or maybe a certain young population in a certain town, and if you repeatedly take a 400 sample size of 100 times, you do have 100 number of times of samples having a 400 size, those 100 samples will not result in exactly the same mean value. Why? Because there is individual variation. That individual variation will lead to sample variation, so that the variation in the result, which is calculated from the samples, is because of sampling variation according to the frequentist approach. So frequentist inference begins by assuming that the null hypothesis is to be true. We begin the null hypothesis is to be true, and then we collect the data. Okay, if the result from the collected data is against with that of the null hypothesis which were assumed to be true, that will be surprising, because we obtain or we get a different result, result which is different from the null hypothesis, that will be surprising. But if the result obtained from the collected data is similar with the null hypothesis, then that is not surprising, because at the very initial point we have already hypothesized, and the collected data is similar with the hypothetical value. That will not be surprising. Okay, so investigators will collect the data after just developing the hypothesis, which is supposed to be true. The investigators will collect the data. The collected data will be analyzed, and they will ask themselves, how surprising is my result if there is actually no effect of treatment? You see, that means the null hypothesis says that there is no treatment effect, it says. But if the collected data indicates that there is effect of treatment, then it is contradicting to the null hypothesis, which were supposed to be true, So that will be a surprising finding. So that will reject the null hypothesis, and then we'll accept the alternative hypothesis. Okay, so the data would be surprising if there was a low probability by chance alone of obtaining another data set at least as extreme as, which is far away from the null hypothesis and are likely to occur by chance. You see, if the p-value is interpreted in such a way, p-value is the probability of getting the observed data purely by chance if the null hypothesis were true. If, by convention, if the p-value is less than 0.05, like for example, if it is 0.03, we can change this in terms of percentage, it is 3%. So how do we interpret this? The probability of getting the observed data purely by chance is 3%. So 1 minus 3%, that is 93%, is real. The observed finding to be real is 97%. And the observed finding to occur by chance, the probability of the observed finding to occur by chance is only 3%. So that the remaining 97% is the probability of the data to occur with reality, That is the interpretation of the p-value. So that if there is a 95% chance of the data to occur with real, and the by chance occurrence is small, so that the observed finding is true, and that is against with that of the null hypothesis. So we'll reject the null hypothesis, and then we'll accept the alternative one. So that is the interpretation according to the frequentist approach, Okay. This probability of obtaining another data set as extreme as the one collected is known as the p-value. And the p-value is often criticized for being misunderstood and misused in the field of medicine or medical research, For example, in contrast to the popular belief The p-value is not a measure of how correct the hypothesis is. You know, the p-value is not the measure of how correct the hypothesis. It is not the measure of the hypothesis, you know. Rather, it is the measure of how likely the observed data is to occur by chance. It is the measure of the data. It is not the measure of the hypothesis. Rather, the p-value is the measure of the data, how the data occurs purely by chance or not. Nor the p-value is not a measure of the size or importance of an effect size, you know. Rather, it just talks about the by chance occurrence of the finding in the collected data. It does not measure how much effective is a drug. It does not tell us the effectiveness of the drug. Rather, whether the observed finding with related to the treatment to occur by chance is some amount of percentage, you know. So in particular, large p-values do not provide evidence of no effect. They do not provide evidence of no effect. Rather, they provide that if the p-value is large, that means the observed finding have occurred by chance. The by chance occurrence of the observed finding is higher. That is the meaning of p-value. Other than this, the p-value does not tell whether there is treatment effectiveness or not. Rather, it is telling about the by chance occurrence of the observed finding. How much is the percentage of the chance occurrence of that result? It is telling about the chance occurrence of the data, not about the treatment effectiveness, you know. That should be just understood in such a way, the interpretation of the p-value in the frequentist approach. So a p-value is simply the probability of obtaining another data set, the probability of obtaining another data set at least as extreme as the one which is collected by chance in this data set. The probability of getting another data set with a similar result to occur by chance is this much percent. Like if it is 0.02, that is 2%. That is the way that a p-value should be interpreted, you know. So for example, suppose we run an analysis and get a highly significant p-value of having 0.001 for treatment variable, you know. There is a treatment variable. So the p-value is 0.001. How do we interpret this p-value now? If you change this in terms of percentage, it will be 0.1%. So formally, it should be interpreted in such a way. There is a 0.1% chance of collecting data equal to or more extreme than this result, the result which is obtained by the current data, if the null hypothesis were true. You see? It would be surprising to collect this data if there is in fact no treatment effect. That means if the null hypothesis were true, simply. So the by chance occurrence of the result for further data that will be collected is 0.1%. So the probability of getting a result or the extreme data having similar result to occur by chance is only 0.1%. Therefore, the remaining 99.9% will be the real occurrence or the probability of the data to occur in reality. So that we are dealing about the probability of the data, not about the probability of the hypothesis or not about the probability of treatment effectiveness, you know. We are talking about the by chance occurrence of the observed finding or the observed result in the collected data. That is the way the frequentist statistics interpret p-values, you know. Okay, if we had run the analysis, another analysis, and if we get a p-value of 0.46, then we change it in the form of percentage, that will be 46%, you know. So that there is a 46% chance of collecting the data equal to or more extreme than this, like for example, if the mean value for a certain medical variable, like serum uric acid level is said to be 6.4, and the p-value is now 46%, that's 0.46. So the interpretation will be, the mean value is 6.4, I said. So the interpretation of this p-value will be, there is a 46% of chance of collecting a data, another data set, equal to or more extreme than these values, 6.4, you see? Chance of collecting the data equal to or more than this value, the value which is obtained by the current data, if the null hypothesis is true. So that there is a high chance of occurrence of the results. That's 46. So the real probability of the data to be true is 1 minus 46. That is 54 only, you know. So that will not be just surprising. So that the observed finding will not contradict with the null hypothesis. So it would not be surprising to obtain these results because at the initiation of the study or the proposal, we have said already in the null hypothesis, there is no treatment effectiveness. So generally the p-value is dealing about the probability of getting the observed result purely by chance if the null hypothesis were true. Okay. So this result is not evidence. This result is not about not about evidence of no treatment effectiveness. Rather, it is about the by chance occurrence of the observed finding. Because the inference begins by assuming that there would be no treatment effectiveness. The null hypothesis says that there is no treatment effectiveness. Even though the null hypothesis starts with there is no treatment effectiveness, the final interpretation of the p-value is not related with no treatment effectiveness. Rather, the p-value is about the by chance probability, the probability of the by chance occurrence of the observed finding, you know. That is the issue that should be understood in such a way. Okay. So the key here is that the probabilistic statement, that is the p-value, can only be made about the data. It is not about the hypothesis, or it is not about the parameter. Parameter, that means the treatment effectiveness, the proportion, the mean. The probability is not, the p-value is not talking about the parameter, you know. It is not about the mean value, the probability of the mean value, the probability of the proportion. It is not about that. The p-value is not about the probability of the hypothesis. Rather, it is the probability of the observed result in the collected data set to occur purely by chance. That is it. So the p-value is the probability about the data. It is the probability about the data. The probability of getting another data set to have an equal result or greater than purely by chance percentage is just the p-value interpretation, you know. So another issue is now reporting a confidence interval can improve the interpretation of results compared with a p-value alone, because the p-value will just tell you that whether how much is it statistically significant or not. That means how much is the by chance occurrence probability of the data. But in the case of the confidence interval, it will show us the level of precision, the width of the confidence intervals, whether it is narrow or wider, how much is precise, and even the direction of the effect, you know, whether it is positive or negative. And it can also tell us what the p-value can tell us. It can be just used to just evaluate whether there is statistical significance or non-statistical significance. Okay. So a 95% confidence interval tells us that if we were to repeat the experiment over and over, infinite number of times possibly, according to the frequentist approach, the 95% confidence interval is interpreted in such a way, you know. 95% of the computed confidence intervals would contain the true mean value or the true proportion value. You see? If you repeated a research 100 times, if you conduct a similar research 100 times, and if you calculate a confidence interval for each of these 100 research works, out of the 100 research work results, the 95% confidence intervals, out of the 100 research finding confidence intervals, the 95% of the computed confidence intervals will contain the true value within the interval, you see. So it is about the computed confidence intervals which could contain the true value. That is the interpretation of the confidence interval in the frequentist approach. We need to understand in such a way, you know. So this is different from saying that there is a 95% chance that the true mean will lie between the interval. You see? If you say that the 95% of the computed intervals will contain the true mean, you are talking about the percentage, how much percentage of the intervals will contain the true value in the first case. But in the second case, if you say there is 95% chance the true mean will lie within the interval, that means you are attaching the probability to the value, to the true value. But in the first case, the probability is attached to the intervals, you know, the confidence intervals. In the second case, the probability is attached to the parameter, the true mean. In the first case, the probability is attached to the confidence intervals or the intervals calculated. You see? So the first scenario is the right way of interpretation for the confidence interval. That means 95% of the computed intervals or confidence intervals will contain the true value, the parameter. That is the correct way of interpretation for the confidence interval. We should not interpret wrongly by saying that there is a 95% chance the true value will be in the confidence interval. It is wrongly interpreted, you know. Because frequentist statistics cannot assign probability to the parameter I cited. The frequentist statistics assign the probability for the data. The 95 out of the 100 research works, each of these 100 research works will have their own confidence intervals. So these are the datas. So the probability will be assigned to the computed confidence intervals. We cannot assign the probability to the parameter. The parameter is the mean, the proportion, the variance, the standard deviation, maybe a standard error. So all these parameters will not have a probability according to the frequentist approach. So frequent statistics cannot assign probabilities to the parameters, you know, to the true mean. That means the true mean either lies within the interval or it does not lie within the interval. That is the incorrect, you know. Rather, we will interpret the 95% of computed confidence intervals will contain the true parameter. That is the correct way of interpretation according to the frequentist approach. What about the Bayesian statistics? In the Bayesian statistics, we assign probabilities for the parameter. That is the reverse of frequentist approach, you know. We assign the probability for the parameters, and we assign the probability for what? For the hypothesis. You see? We do not assign probability for the data according to the Bayesian statistics. That is the difference between the frequent statisticians and that of the Bayesian. So Bayesian statistics are named after the Reverend Thomas Bayes, whose term describes that a method to update probability based on the data and past knowledge, you know. So the posterior distribution or the posterior probability will be updated always as there is a new data and new knowledge is generated, So the posterior probability will be calculated or updated by the use of the current data with that of the past knowledge or the prior distribution according to the base or the Bayesian statistics. There is always prior distribution and posterior distribution. That prior distribution is the information which is collected from different literatures. Like, for example, the prevalence of a certain disease in a certain community, which has been reported by a DHS report in before 5 years or maybe 2 years. That will be taken as the prior distribution or the probability of having a disease. And the currently collected data will be added upon the past information, that is the past prior distribution, in order to update the new probability distribution about having a probability of that specific disease. So there is a prior distribution and a posterior distribution in the case of Bayesian statistics. But in the case of frequency statistics, there is only one distribution, which is the posterior distribution, which is developed by the use of currently collected data. So this Bayesian statistics, in contrast to the frequentist approach, the parameters and the hypothesis are seen as the probability distribution, and the data is the fixed one. According to the Bayesian statistics, we do not have infinite number of possible number of data, We do have only one data set, and that one data set is the one which is collected, the collected data set, according to the Bayesian statistics. And then the probability distribution will be assigned for the parameters that we are going to estimate. The parameter is to mean that the mean value, the proportion, the variance, the standard deviation, whatever. And the probability is again assigned for what? For the hypothesis that has been developed. So now in the Bayesian statistics, the probability is assigned for the parameters and for the hypothesis. In the case of frequentist approach, the probability or the probability distribution is assigned for what? For the data. In the frequentist approach, the probability distribution is not assigned for the parameter and for the hypothesis, but it is the case for Bayesian statistics. So this idea is perhaps more intuitive, or that means more natural, because generally the data we collect are the only data sets that we have. The uncollected possible number of infinite data sets are not on our hand, The data that we have already, that is already collected is the only data set that we have on our hand. So it does not necessarily make sense to perform statistical analysis, assuming that it is one of many potential data sets, according to the Bayesian statistics. So only we do have one fixed data set, and that one fixed data set is the one that is already collected, which is more intuitive or more natural. So for the formula for calculation of the posterior probability of Bayesian distribution is given here in this slide, Okay, so the probability distributions summarize the current state of knowledge about the parameter, or the probability distribution about a hypothesis, you see? So the probability distribution is assigned for what? About the parameters that we are going to estimate, or about what? About the hypothesis. And the probability distribution can be updated, can be updated as more data becomes available. So the probability distribution will be always changing, because as per the data becomes more available, then the posterior distribution will be updated. It will be changed again and again as per the data is becoming more available. So to do this, updated for posterior distribution of the probability, we use this formula. The probability of theta given the data is equal to the probability of the data given the theta, the probability of just the disease theta The probability of having the disease or theta given the data that have been already collected currently is equal to the probability of the data given the disease, the probability of having the disease or the probability of being positive for a certain test result, that is the data, given that there is among the individuals with the disease, that is the theta, multiplied by the probability of the having the disease previously, that is the probability, the prior probability or the prior distribution, that is P of theta, over the probability of the data, the probability of the data to be positive. For example, if you are just conducting any screening test. So generally, this is a formula for a Bayesian probability distribution. So the probability distribution that summarizes what is known about an outcome before a test, that is the prior distribution, or that is a piece of information is obtained, is known as the prior distribution. And such an outcome may be the prevalence of a disease, which has been reported by different organizations. So the prior distribution or the prior probability of the outcome theta, like having the probability of having the disease, is labeled as probability of theta. The probability of having the disease, that is probability of theta, Now, the prior is one of the key differences. The prior distribution is one of the key differences between the frequentist statistics and that of the Bayesian statistics. So frequentist analysis base their result only on the data. But in the Bayesian analysis, the probability distribution is based upon the prior distribution with that of the collected data. So the prior data or the prior distribution could be formulated by expert beliefs or by historical data, or maybe by the combination of the two, So we need to just refer back to the historical data from different literatures, or maybe from expert beliefs. So now let's consider this example. What is the probability of having the disease, that is theta, given the new data? That means the test was positive. If you have learned in screening, like for example, two of the properties for a screening is sensitivity and specificity, Sensitivity is the ability of the test to identify correctly those individuals with the disease. But in the case of sensitivity, there will be true positives and false positives, So any test which says positive is not 100% indication of having the disease, So what will be the probability of really having the disease given the test is positive? So the notation for this scenario, that is P in bracket theta / test positive, is that the probability of having the disease given that the test is positive. Out of those which has been said positive, how many of them are really having the disease? That is it. So in Bayesian terminology, this probability is known as the posterior distribution because the test has been already done, The test has been already done. So the test has been already done. That means the data is already collected. So out of the positive test results, how many of them are really having the disease? The probability of having the disease, given that, provided that the test result is positive. Out of those which have been said positive, how many of them are really the disease? That is a posterior distribution. And this summarizes what is known as about the outcome using both the prior information and the new data. The new data is the data obtained by the test, the diagnostic test. But the prior information could be obtained by referring back to different literatures. Maybe the prevalence of the disease, the previous prevalence of the disease from different sources, So among all the potential patients, regardless of whether they have the disease, the population at risk, that means, the probability of a positive test, that is true positive plus false positive, is the probability of a test to be positive is labeled as the probability of the test to be positive. So this test positive could include both true positives and false positives. You see, that is labeled as the probability of the test to be positive. Okay, therefore, the relative probability of having a positive test, if a patient is truly positive versus the probability of someone randomly selected from the population who may or may not have the disease, having a positive test result is the ratio of the two. That means the probability of the test to be positive among those individuals with the disease divided by the probability of the test to be positive among all individuals, among randomly selected individuals, whether they do have the disease or not. So this is the ratio of the two. The probability of the test to be positive among those individuals with the disease divided by the probability of the test to be positive among the population at risk. That is the ratio of the two. So the posterior probability of having the disease, if you have a positive test, is then the baseline prevalence of the disease in the population. That is the prior probability. So the posterior probability of having the disease, if you have a test positive, is the baseline prevalence of the disease in the population multiplied by this factor, the prior information, that is the prior distribution, or the prior probability of having the disease multiplied by the ratio of this, by this ratio. That will be the posterior probability. That will be the posterior probability. Now, let's have this example to make it clear, a COVID-19 test. Let's assume that a test for COVID-19 infection is 100% sensitive, so that there is no false positive in this case. There is no false negative. There is no false negative because the sensitivity of the test is 100%. So an individual which is said to be positive by this test is really positive. There is no false negatives according to this criteria. But therefore, that means the probability of the probability of the test to be positive among those individuals with the virus is 1. That means 100% because the sensitivity is 100. And now let's assume that there is a 99.9% or chance of correctly identifying someone who do not have the disease. That is, the specificity is 99.9%. Okay, if you subtract this 99.9 from 100, that will be 0.1. So, a specificity, as you know, is that the ability of the test to correctly identify those individuals without the disease, without the disease. Okay, so if the specificity is 99.9%, so the test will identify correctly those individuals without the disease 99.9 times. But the remaining, that is 0.1% of individuals will be labeled as false positives, because it only correctly identifies those individuals without the disease in terms of 99.9%. So the remaining 0.9% individuals will be said or labeled as positive. That will be false positive. So there will be a 0.1% of false positive if the specificity of the test is 99.9%. So that the probability of the test to be negative among those individuals without the virus is 0.999. You can change this percentage into decimal place, So the probability of the test to be negative among those individuals without the disease, without the virus, is 0.999. Okay, now, the probability of the test to be positive among those individuals without the disease, that is the false positive rate is 0.001. You can change this percentage into decimals, you know. This is the false positive probability. Among those individuals without the disease, this much percent, 0.1% of the individuals will be falsely positive, you know, will be made positive falsely by the test. Okay, now let's proceed. That sounds like a high probability, but what we are really interested is if you have a positive test result, if you are said to be positive for a test, how likely it is that you actually have the virus. The probability of having the disease, the virus, given the test is positive. Out of those individuals which have been positive, said by positive by the test, how many of them have really the disease? That is the one that we want to know. So now let's just put this in terms of formula, you know. So we can calculate this probability by using the Bayes theorem or the Bayesian probability theorem, you know. So the probability depends on the probability of having the disease depends on two components, you know. One, prior information, the prevalence of the disease, the prior prevalence of the disease. That is the prior distribution or the prior information, which will be obtained from different literatures. That is the probability of having the disease prior to the test. Before we do a laboratory test, the probability of the patient to have the disease is determined by the prior prevalence of the disease, you know. That is the prior information or the prior distribution. How likely you were to have the virus? That is the probability of having the virus before taking the test, before the test was done. Just by having simply, by taking physical history of the patient, by doing physical examination, what will be the probability of having the patient, the probability of the patient to have the disease based on the historical data that we have. So this will be calculated with this formula. The probability of having the virus, given that the test is positive, now in addition to the prior information, the test has been already done. So the posterior distribution will be calculated by a combination of two informations. One, the prior information, that is the prior distribution, and two, the test, the currently collected data by the diagnostic test. So that the probability of having the virus, given that the test result is positive, you have been tested by a certain screening method, and the result is saying that its side is positive. So what will be really the probability of having the disease, given that the test result is positive, is calculated by this formula. The probability of the test to be positive among those individuals with the virus multiplied by the prior information, that is the probability of having the virus based on the prior information, based on the prior prevalence of the disease, over the probability of the test to be positive among the susceptible individuals or the population at risk. So this is the way how we can just determine the probability of having the disease, given that the test result is positive and then based on the prior information. So the probability of having the virus, given that the test result is positive, is calculated by the use of this formula. That means the probability of the test to be positive among those individuals with the virus multiplied by the probability of having the virus based on the prior information over divided by the probability of the test to be positive among the population at risk. That is it. So if we assume that the prior probability is the prevalence of the virus in the population, maybe at the height of the pandemic, during the pandemic era, which is 2%. Let's say that the prevalence was 2%, obtained from maybe some source, you know. So that the prior probability of having the disease or the virus is 0.02. So this is the probability of having the virus, the prior information, which is obtained by the prevalence of the disease from different sources, you know. So that is the prior information or the prior probability of having the disease. So without testing an individual, if an individual comes with sign and symptom of COVID-19, before doing any test or a laboratory test, the patient will have a probability of having a disease of 0.02. That is based on the prior information. Now, in addition to the prior information, the test will be conducted, you know. So that according to this prior information or prior probability of having the disease, if we do have 1 million population or 1 million people, you multiply this 1 million by 0.02, so that how many of them will have the disease based on the prior information. If you multiply this 1 million individuals with 0.02, that is the prior information, so that 20,000 of these 20,000 of these people out of 1 million will have the virus. Based on what? Based on this prior information or prior probability of having the disease. Because the prevalence is 2%, so the probability of having the disease based on the prior information is 0.02. So if we do have 1 million individuals, you multiply this probability, that is 0.02, by 1 million, so that it will be 20,000. 20,000 of the individuals will have a COVID-19 based on the prior information. So if you subtract these 20,000 individuals who have the disease out of the total individuals, that is out of 1 million, the remaining 980 individuals will not have the disease. Will not have the disease, you know. By subtraction of those individuals with the disease based on the prior information. Okay, so now let's proceed. So have in your mind that 20,000 people will have the disease, the remaining 980 will not have the disease. Based on what? Based on the prior probability, the prevalence of the disease, that is 0.02, the probability, or 2%. Okay, let's continue now. If we test them, if the test will be done then again, this is based on the prior information, you know. If the test is going to be done now, and if we test this 20,000 of individuals with the disease, all of them will be positive because the sensitivity is 1, you know. Remember that the sensitivity is 1 or 100%. If we test them, all 20,000 individuals will be positive for the disease. That is true positive. Because we have said that the sensitivity of the test is 100. Okay. But the remaining, another calculation, you know. Let's proceed. Okay, let me go back to the previous slide. Over here, we have said that 20,000 of them will have the disease. And if we test them, the 20,000 of these individuals will be positive for the test because the test is 100% sensitive. There will not be false negatives in this case. Okay. But the specificity is 99.9%, you know, or 0.99. And there is 0.1% or 0.001 probability of falsely positive results will be there among those individuals without the disease, you know. So if you multiply this 980,000 by 0.001, so that you will get a false positive numbers. Out of those individuals without the disease, 980 of them will have a false positive result. Out of 980,000 multiplied by 0.01, these were without the disease, you know. But out of this, 0.001 of them will be falsely positive because the specificity is not 100. 99.9%. So 1 minus 99.9, that will be 0.01 or 0.001 in terms of probability. So out of those individuals without the disease, if you multiply this probability, 980 of them will be falsely positive. So the number of positive results will be 20,000 plus 980. So there will be 20,980 positive test results will be. Both true positives and false positives. Okay, now if you subtract this 980 from 980,000, true negative results will be 979,020. So these individuals will be true negatives. Because you need to subtract out of the total negatives, the false positives will be subtracted from the total number of negative individuals. So the true negatives will be the subtraction of the two, this much. So that the total number of the total number of positives, both true positive and false positive, will be the summation of the two. Okay. So that the probability of the test to be positive is the total number of positive results divided by the population at risk. That is, the total number of positive results is 20,980 divided by the population at risk is 1 million. So that the probability of the test to be positive is 0.02098. Okay, now have this in your mind. And the chance of having the virus giving a positive test. You see, the probability of having the virus given the test result is positive will be determined by using the second equations that we have in the previous slide, that we have seen in the second slide, in the previous slide. So, the formula that we have already placed over here, the probability of having the disease, the virus, given the test result is positive is equal to the probability of the test to be positive among individuals with the disease multiplied by the prior probability of having the disease over the probability of the test to be positive among the population at risk. This is a formula. So we'll just substitute those numbers within this formula, So now let's substitute these numbers. So the probability of having the disease, that is the virus, given that the test result is positive, is equal to the probability of having the disease out of those individuals with the disease, the 20,000 individuals. So the probability of the test to be positive among those individuals with the disease is 100, because the sensitivity is 100. We have said that. 1 multiplied by the probability of the test or the probability of having the disease based on the prior information, that is 0.02. The prior probability, based on the prevalence of the disease. Over the denominator is here, this one. The probability of the test to be positive among the population at risk, which is 0.02098, this one. So that the probability, that is the posterior probability. The posterior probability is the probability of having the disease after the test is done, is equal to 95.3%. So if a test is positive for an individual, 95% of the result is indicating that the individual will have the disease. So that is approximately, there is 95% of having the disease. So in this setting, if the test is positive, one should believe the result. So you see the posterior probability, that means the probability of having the disease, is determined by the current probability of having the disease, this one, the probability of the test to be positive among the population at risk, which was obtained by doing a laboratory test, and then by the prior probability of having the disease based on the previous prevalence of the disease. That is the Bayesian statistics. So the posterior probability is determined by the current data, the probability attached with the current data plus the probability of having the disease based on the previous information. So this is the probability or the posterior probability, how it will be calculated by the Bayesian statistics approach, Okay. And actually this is very common in clinical epidemiology. If you have taken the course clinical epidemiology, this will be very easy for you. So however, now let's just change the prevalence of the disease, the prior information, Now look at the posterior probability for this Bayesian statistics is now 95%. As the data, the prior information is changed, the posterior probability will be changed. So let's check. In the previous example, we have seen that the prevalence is 0.02 or 0.2%. Now, what if the prevalence of COVID-19 was estimated to be much less, from 2% to that of 0.2%? Previously, we have said that it is 2%, or in terms of probability, it is 0.02. Now, let's assume that the prevalence has been found to be 0.2. So the probability of having the disease based on the prior information or the prevalence of the disease is 0.002 in terms of decimal place. Such as during a period of maybe governmental stay-at-home period, which has been declared in the past, maybe 6 or 5 years ago. So now, in this scenario, and mind you that the sensitivity and the specificity are the same. The sensitivity is 100 and the specificity is 99.9. It remains at the same with the previous example, What is being changed is the prevalence of the disease. That is the prior information or the prior probability of having the disease. So now, in this case, if you multiply the 1 million individuals with 0.002, so that 2,000 individuals will have the disease. You see, previously 20,000 individuals were having the disease. But now in this case, because the prevalence of the disease has dropped from 2% to 0.2%, the number of individuals having the disease will be 2,000. Okay, so they will have a true positive test result, because the sensitivity is 100. If we test them, these 2,000 individuals, they will be positive for the disease. Okay. So now let's proceed again. The remaining 997,002 will have a true negative result. Why? Because if you multiply 1 million individuals with 0.999, the previous specificity. So, and then the remaining 0.001% is just false positive result out of the negative individuals, So that if you subtract 2,000 individuals from 1 million individuals, so that the total number of negative individuals will be 998,000 will be negative. But 998,000 multiplied by 0.001 will be a false positive, because the specificity is 0.999. The remaining 0.001 will be a false positive result. Okay, therefore, when you multiply this 998 or 998,000 by 0.001, so that 998 individuals will have false positive result. So the total number of false results will be 2,000 plus 998. Okay, if you subtract this 998 from 998,000, the true negative result will be this one. Okay, so the total number of positive results will be the summation of 2,000 and 998. Okay, so giving 2,998 positive results. So that the probability of the test to be positive among the population at risk will be the total number of positive results divided by the population at risk. So the probability of the test to be positive is 0.002988. Now let's substitute this number with the previous formula. The probability of having the disease, the virus, given that the test result is positive, is the probability of the test to be positive among those individuals with the disease, that is 100 or 1, multiplied by the probability of having the disease based on the prior information, that is the prior probability of having the disease, which is 0.002 over here. Over the denominator is most important here. The probability of the test to be positive among the population at risk, which is 0.002988. So that, in this case, the probability of having the virus, given the test result is positive, is almost 67%. You see how the posterior probability of having the disease has been changed from 95 to that of 67%. When the prior information is changed, that is the prevalence of the disease. You see the posterior probability of a Bayesian statistics will be updated and changed as per the data is changing, the prior information is changed. So that is the way how the Bayesian probability will be calculated. So that, and the probability is always attached with the parameter, the probability of having the disease. Okay, so this is all about maybe theoretical issue for the Bayesian statistics, So in this scenario, which is the probability of having the disease is 67, one may truly question whether a positive test result is an indicative of diagnosis of the infection or not. Because it is 67%, How could we believe? So the test would be under question mark. Because there is a false positive result, approximately 1 out of 3, Out of 3 individuals, 1 will be falsely positive. Among 3 negative individuals, 3 individuals without the disease, 1 of them will be just labeled as falsely positive. So this will be questioned. So the percentage of, or the probability of having the disease has been dropped from 95% to that of 67%. When the prior information, the prior probability of having the disease is changed. That is the prevalence of the disease. So that is how the posterior probability will be updated as per more data is available, more previous information is available for the Bayesian statistics, Okay, on the other hand, if we were testing hospitalized patients, the prevalence would be expected to be much higher, If the patients are hospitalized because of COVID-19, then it is expected that the prevalence will be high. And there would be a lower chance of obtaining a false positive result, The true positive results will be higher. So that this simple calculation highlights the importance of taking into account prior information. You see? This demonstration of example dataset is to just show you how it is important to take into account prior information for the calculation of posterior probabilities, in which something that frequentist statistics does not do. That is the very basic difference between the two. Okay, sometimes, formulating a prior information is not that easy and it is not clear. And in such cases, if there is no easy way of getting prior information, the use of priors can be seen as a drawback of Bayesian inference, And particularly when results depend on the chosen prior. If the posterior probability is dependent on the prior information, and if the prior information is not clear, so that the result will be under question mark. Thus, therefore, the analysis could be manipulated to get a positive test result, So in such cases, an informative prior information should be used in the analysis. An informative priors that provides no additional information could be used. or multiple prayers could be tested to determine the sensitivity of the test for a particular prayer, you know. So, similar with all other analysis methods, it is vital that researchers or investigators should be transparent, and we need to just write all the procedures that have been done in the method section, and with regard to the assumption for the statistical method should be clearly written in the document. And we should be transparent, you know, for the readers to judge our work. So the posterior distribution captures our updated estimate of the probability of the outcome after incorporating of a new data, which is collected by the current data, and including our uncertainties, and can be analyzed to give various statistics, such as the mean and the 95% confidence interval for the mean. So that the prior probability, the posterior probability of the Bayesian will be calculated by consideration of the prior probability with that of the current data to calculate the parameter with the confidence interval. So the 95% confidence interval is different from the frequentist approach in the case of the Bayesian, you know. Because in the Bayesian approach, the 95% confidence interval will be interpreted, you know, in such a way. It is the parameter that is going to be estimated, or the mean value or the proportion. The parameter range that has a 95% probability of including the true parameter in the case of Bayesian statistics. So the confidence interval have a 95% of including the true value. It is to mean that. But in the frequentist confidence interval, it is often misinterpreted in such a way. One must remember that the 95% confidence interval assumes that the experiment is hypothetically repeated over and over, possibly in infinite number of times. And the 95% of the computed confidence intervals will contain the true mean. That is it. But in the case of the Bayesian analysis, the confidence interval, the calculated confidence interval, have a 95% of probability of containing the true mean. That is the interpretation in the Bayesian. But in the frequentist approach, 95% of the confidence intervals will contain the true mean. That is the frequentist approach. But in the case of the Bayesian analysis, the confidence interval, the single confidence interval, the calculated confidence interval, have a 95% of probability of containing the true value, the parameter. That is the difference between the two in the case of interpretation of the confidence interval, you know. So one of the big disadvantage of, the advantage of Bayesian inference is that the posterior distribution can also be used to directly calculate the probability of different hypotheses, you know. Not only the parameter, but also the probability can be attached to the hypothesis. That means the hypothesis says that we can say, if the hypothesis says that there is no difference between two treatments, the alternative will say that one treatment is better than the other treatment, or there is a difference between two treatments. So we can assign a probability directly to this probability. One treatment is superior than another treatment. The probability of treatment 1 to be superior than the other treatment is this much %, we can say, in the case of Bayesian analysis. That is the advantage of Bayesian analysis. So in this respect, Bayesian inference is more natural or intuitive at its core and is closer alignment with our natural mode of probabilistic reasoning, you know, than the frequentist approach. Because we people are naturally intended to just say that this is better than the other. Rather than saying 95% of the computed confidence intervals will contain the true value, it is better to say naturally one treatment is better than the other. That is the advantage of Bayesian analysis in terms of interpretation, you know. For example, we are more interested in the probability that one treatment is superior than the other, which is the Bayesian interpretation, than in the probability of obtaining certain data, assuming the treatments are equal. That is the frequentist approach. You see? the probability of getting the observed result purely by chance if the null hypothesis were true, that is the frequentist one. So, but in the case of Bayesian analysis, treatment 1 is superior than treatment 2. This is more natural, you know. So this is better than the frequentist way of interpretation. So this advantage in interpretability of the results remains even if our analysis uses an informative prior, you know. Even if there is no informative data for Bayesian analysis, the interpretation still remains there. You see? So the posterior distribution, yeah, how the posterior probability distribution will be calculated in the Bayesian analysis is by the use of MCMC, that is the Markov chain Monte Carlo method. That is the issue for the posterior distribution calculation, you know. So this Markov chain Monte Carlo, abbreviated as MCMC, iteratively samples different positions or parameter values in hypothetical posterior distribution using a set of rules, you know. So at each new position, we calculate the ratio of the new posterior probability to that of the previous position. So if the ratio is greater than 1, we accept the new position and then reject the previous one. But if the new position or if the new probability distribution is less than the previous one, then we'll reject the new position and accept the previous one. So this is a way how the MCMC will just do. Maybe similar with the maximum likelihood estimation and estimation of parameters for the frequentist approach. In the Bayesian analysis, we use the MCMC approach, you know. Okay, so now in order to just summarize the comparison of this Bayesian analysis with that of the frequentist analysis. So both the frequentist and the Bayesian analysis are useful for data analysis, you know, as long as they are interpreted correctly. But we should take care of interpretation of the results. So the strength of the Bayesian approach is the incorporation of prior information and the ability to directly calculate the probability of different hypotheses, the ability of attaching the probability for the hypothesis and the attaching the probability to the parameter. That is the advantage of the Bayesian analysis, you know. So as we have seen previously, the p-value is calculated from sampling in the case of frequentist approach. So it is interpreted in such a way, given the null hypothesis, the frequency of finding a significant result is this much %. That has been already said, you know. So a p-value is the probability of getting the observed result or more extreme data under the assumption that the null hypothesis is true. That is the frequentist approach. But in the case of Bayesian, as opposed to the frequentist approach, which is based on the infinite number of repeatable events, the Bayesian statistics relates with subjective belief. That is, Bayesian statistics uses the idea of updating beliefs with new information when testing a hypothesis. So it attached the probability to the hypothesis, you know. So Bayesian statistics uses the idea of updating beliefs or updating posterior data or posterior probability with a new information and that of a prior information. So here is a formula actually, the base factor with the belief. So now the probability distribution will look like this one for the Bayesian statistics. If we do not use any prior data, that is, if there is an informative prior belief, so that the curve will look like this. And then if we do have a prior information, so that the posterior distribution of the curve for the Bayesian analysis will look like this one, you know. So the difference between the two is that the p-value is the probability of observing the data purely by chance if the null hypothesis were true in the case of the frequentist one. But in the Bayesian analysis, probability is an expression of a degree of belief of an event, you know, based on your prior knowledge. So the p-value is the probability of the hypothesis given the data, or the probability of the parameter given the data. That is the interpretation of the p-value in the case of Bayesian analysis. Okay, Here is a summary of the comparison for that in terms of the interpretation of the p-value and in terms of the interpretation of the confidence interval between these two approaches, you know. So it is more, that means the strength of the Bayesian approach is that the incorporation of the prior information, as I have said before, and that of the ability of attaching the probability to that of the parameter with that of the hypothesis. So this is all about the Bayesian statistics approach. Thank you very much.